In this lecture, we'll continue to explore the alkane functional group. We're going to cover the topics of conformations, and we'll go into more detail on nomenclature. When we refer to a molecule's conformation, we're actually referring to the form the molecule can take. A conformation is essentially a shape or arrangement of a molecule. And what we'll learn is that in many organic molecules, especially in alkanes, there can be many different conformations, or many different ways that a molecule can appear in 3 dimensions. This comes from the fact that single bonds, including carbon-carbon single bonds, are able to rotate or spin freely. This means that when you have a molecule that has one or more carbon-carbon bonds, the atoms connected by those bonds are able to rotate. They're able to change conformations. The result of this is that the more single bonds that are present in a molecule, the more conformations that molecule can take. Let's look at some models to understand how this happens. We already know that alkanes contain many different single bonds. Even the simplest alkane, methane, contains 4 single bonds, each one between carbon and hydrogen. All single bonds are capable of rotating, meaning that I can spin each one of these bonds freely. However, turning these hydrogen around doesn't really change anything about the shape or the conformation of the molecule. Its geometry is still tetrahedral, and that's due to VSEPR theory, or the repulsion of the different bonds in the molecule. Something more interesting happens, however, when we try this on larger molecules. This is a molecule of ethane. We already know that ethane contains 2 carbons bonded together through a single bond. Just like with methane, I can freely rotate these different hydrogen bonds, but I can also rotate the carbon-carbon bond. The consequence of doing this is that you get what looks almost like a propeller-like action, whether we look at it from the side or whether I rotate this molecule so you can see it from the front. This allows the carbon-carbon bond to rotate freely in space. And in fact, this is happening all the time when we have molecules that have carbon-carbon single bonds. There's different conformations. There's conformations where we see that each one of the bonds appears to be staggered. There's also conformations where it's as if each one of the bonds is lined up. Perhaps the molecule that this is most easy to see this with is butane. Here's a molecule of butane. Butane contains 4 carbon atoms. Each one of these carbon-carbon bonds can rotate. And as you can imagine, that can get pretty complicated. So if you play with the model kit on your own time, you'll see there's many different ways I can turn this molecule. But let's just look and focus at this carbon-carbon bond in the middle for a second. When I rotate this carbon-carbon bond, the effect is just like when I rotated ethane. I get essentially a bit of a propeller. But because there are other carbons connected to this second and third carbon in the molecule, the effect is much larger. Notice that in this position, I have 2 carbons that are right next to each other. They're both pointing up as I'm holding the molecule in this position. But as this carbon-carbon bond rotates, I can get into a different conformation that allows those 2 carbons to be much further separated from each other. When the carbon-carbon bonds are further separated from each other, it puts space between the electrons on the first carbon and the electrons on the 4th carbon. The consequence of this is that it allows those atoms to be further apart and therefore to become more stable. So many organic molecules can actually exist in multiple conformations. In fact, the more single bonds that a molecule has, the more ways that molecule can twist and contort, and the more conformations will exist. In the case of butane, we saw that one possible conformation allows the first carbon and the 4th carbon to essentially be on the same side of the molecule. In this case, they're both pointing up. Another conformation exists when the first carbon and the 4th carbon point in opposite directions. When the first and 4th carbon are lined up on the same side of the molecule, we call this a syn conformation. If we were drawing this with a Lewis structure, it would look like this. When the first and the 4th carbon go in opposite directions, this is called an anti-conformation. And as a Lewis structure, it would look like this. Even though butane can exist in both of these conformations, as well as every rotational angle in between, it'll spend most of its time as the most stable conformation. For all molecules, the most stable conformation is the one that has the lowest energy. And the lowest energy results from minimizing any possible electron repulsion. Remember that electrons exist around all of the atoms and in the bonds in an organic molecule. So the more we spread out the atoms and bonds in a molecule, the more we minimize electron repulsions. The anti-conformation is more stable for this reason. In the anti-conformation, we've essentially spread out the carbons better than if we have a syn conformation, where both carbons are on the same side of the molecule. Remember, however, that one molecule can have many conformations. It's simply that it'll spend most of its time in the most stable conformation. In fact, this explains a little bit of why alkanes are so stable when they form a zigzag structure. The zigzag structure is actually an anti-conformation because it keeps the carbon chain as far apart from itself as possible. The syn conformation, on the other hand, would actually put the chain closer together, and that's less stable. One more note about conformations. It's important to remember that both of these molecules are butane. They're still the exact same molecule. There's no way you can isolate these two molecules because in a sample of butane, if you had 100 molecules of it, most of them would be in the anti-conformation, but they would constantly be rotating and switching back and forth. Unlike conformers, which are really just the same molecule twisted into different arrangements, isomers involve a more substantial difference between structures. Let me show you an example. Consider the chemical formula C2H4Cl2. Based on what you know about chemistry, take a second, pause the video, and draw a possible structure for a molecule that has that formula. You may or may not have noticed that there's actually more than one correct way to do this. One option, which you may have chosen, is to connect the two carbons together and then to put a chlorine on each carbon. That means that each carbon will also have two hydrogen. Remember, it doesn't matter whether your hydrogen point up, down, or to the side because the single bond between the carbon can rotate. But what does matter is in this particular structure there's a chlorine attached to each carbon. This is a correct structure for the chemical formula C2H4Cl2. You may have written this structure or you may have written a different structure. The other possibility is to connect the chlorines to the same carbon. This means one carbon will have one hydrogen and the other carbon will have 3 hydrogen atoms attached to it. These are different structures. They're completely different molecules. They're not conformers because I can't just rotate some bonds. If I was making a model, I'd have to actually break apart the model and put it back together differently. If I was drawing this on paper, as I just did, I'd have to actually erase some atoms and rearrange which atoms are connected to which. Because the structures of these molecules are different, these are what are called structural or constitutional isomers. Essentially, they're molecules that have the same chemical formula, but a drastically different structure. Keep in mind, this is different from conformers because we haven't just twisted our molecule around, we've actually changed its structure. This has a major significance in organic chemistry because when you change the structure of a molecule, not surprisingly, you change its properties. You change everything from its name to the functional group that might be present, and that can have pretty drastic consequences. One of the most classic examples of structural isomerism is from the chemical formula C2H6O. There are 2 different compounds that can arise from this chemical formula. The fundamental difference between the 2 compounds is whether the oxygen is connected to a carbon on each side or whether the oxygen is located at the end of a chain of carbons. If the oxygen is located between two carbons, with a carbon on each side, this is what its chemical structure will look like. If the oxygen is located at the end of a chain of carbons, this is what its structure will look like. These are structural isomers. They share the same chemical formula, but they're connected differently. There's a different order to how the atoms are connected. They're also very different molecules. The molecule on the left has a functional group called the ether functional group. Many chemists would refer to this molecule as dimethyl ether. It's a gas at room temperature, and it has been used as both an industrial propellant as well as a refrigerant. Let's contrast that with the compound on the right. The functional group that's present in this compound is the alcohol functional group. Specifically, this is what's called ethyl alcohol, or simply ethanol. Ethanol is a liquid at room temperature, and we know it as an intoxicant because it's what's present in beer, wine, and liquor, but it's also used as a fuel additive. These two compounds share the same chemical formula, but they have little else in common. It's a classic example of structural isomerism. Now we come to a topic that we'll be revisiting many times this quarter, the topic of nomenclature, or how we name molecules. In organic chemistry, we use IUPAC nomenclature. IUPAC is an acronym which stands for the International Union of Pure and Applied Chemists. IUPAC is essentially a governing body. It's based in Zurich, Switzerland, but it's made up of dozens and dozens of chemists from all over the world. And these are the people that rule on controversies in the chemical fields. Everything from what the atomic mass of an element is to what its name will be on the periodic table of the elements. IUPAC nomenclature, which is sometimes referred to as systematic nomenclature, is a way of naming molecules that has a goal that each molecule that can exist in the universe will have its own individual and unique name. In other words, the goal is that if you use IUPAC nomenclature, you'll always get the same name for a molecule, and no other molecule with a different structure could possibly also have that name. Many organic chemistry students come to love IUPAC nomenclature because it is essentially a really geeky party game. You get a structure of a molecule, and based on a set of rules, you come up with a very unusual sounding name. Or you can reverse the process. Simply by reading the name and understanding the parts and the rules it came from, you can actually draw the structure of that molecule out. This is a major advantage on some of the other types of names that exist, in addition to the systematic IUPAC names. Let's look at one molecule as an example. This relatively simple organic molecule actually has some pretty profound physiological effects. This molecule is what you probably would refer to as ibuprofen. When you say the name ibuprofen, you're referring to a name that was devised by the chemist that originally found ibuprofen, which was patented in 1961. But what does the name ibuprofen mean? Well, you'd have to look that up. It doesn't have any profound physical meaning. And in fact, if I said, draw ibuprofen, there's no way the name can tell you exactly how to draw it. Another name type that we'll run into occasionally are trademark names. So you might be familiar with ibuprofen when it's sold as Advil or Motrin. These are trademarks, so they're generally only used by the companies that own them. And again, they don't give you any information about the actual structure of a molecule. This is where IUPAC naming or IUPAC nomenclature comes in. IUPAC nomenclature is used by chemists all over the world to name molecules. The good side of IUPAC nomenclature is that it's very systematic and it's pretty much foolproof as long as you apply the rules correctly. The downside is the names don't sound so great when you read them out loud. They're more commonly used for writing down names. The IUPAC name for ibuprofen would be RS-2,4,2-methylpropylphenylpropanoic acid. It doesn't exactly roll off the tongue. But unlike the common names and trademark names for a molecule, if you know enough organic chemistry, someone could give you that name, and with nothing but a pen and paper, you could then instantly create the entire structure from the molecule. and you'll be surprised by how easy that actually is to do as we learn these names. We've actually already seen IUPAC nomenclature when we learned how to name straight-chain alkanes. So when it came to alkanes that simply went in a zigzag line with no branching, we learned that these things can have names like methane, ethane, and so on. Branched alkanes, on the other hand, don't have just a zigzag shape because at some point each one of these carbons could be connected to several other carbons. There might be one branch. That branch might have one or more carbons, or there might be other branches. It just depends on the individual molecule. As we've seen, straight chain names involve nothing more than a prefix and a suffix. So names like methane or ethane, because they involve a prefix that tells us how many carbons we have and the suffix ane. Branched names, on the other hand, are going to use these straight chain names as a base, and then they're going to add additional information. So you may think of a branched name as having two parts. One part is the backbone of the molecule, or the straight chain itself. The other part is the information about the branches. And if you think about it, there's really two pieces of pertinent information. One is the length of the branch, how many carbons are in it, and the other is the location of the branch. I've provided a printout on our website of the molecules that I'm going to use for the next several examples. You're welcome to print that out so that you can save yourself some writing, or you're welcome to simply copy down these molecules as we go through them. Remember, you can always pause the video if you need more time to get something into your notes. The first molecule that we're going to do is this one. If you're using the printout, find it on the page. If not, take a second and copy this into your notes. Because this is our first molecule, I've kept it fairly simple. And what we're going to do is go through the individual steps that you'll need to correctly name this alkane using IUPAC nomenclature. The first step, and this will be the first step pretty much for the rest of the quarter, is to find the longest carbon chain. In other words, where can you start with a carbon and move through a chain of carbons to get the longest chain possible? I'm going to use the highlighter, and lots of students find that it's very helpful to highlight as you're naming these molecules. On this one, hopefully it's fairly obvious. The longest chain starts with the carbon on the far left, and I've highlighted it through the carbon on the far right. Now we're going to name this chain. How many carbons are in the chain I've just highlighted? There's a total of 6 carbons. So this part of the name will be hexane. Hex for 6 and ane because we're dealing with an alkane. Now we're ready to talk about the branch. Notice that the highlighting only covers 6 of the 7 carbons in this molecule. I haven't talked yet about this branch. We need to determine the position of the branch on the backbone. In other words, we have to say which carbon it's actually connected to. To do that, I'm going to number each of the carbons in the backbone, and I want to do this so that the branch has the lowest number possible. That means sometimes you'll number from the left, other times you'll number from the right, and depending on how the molecule is drawn, you may have actually started numbering at a top or a bottom carbon. Let me show you the two possibilities. One possibility is this. First carbon would be here, second, third, fourth, fifth, and sixth. If I do the naming this way, you'll notice that that branch that I've circled exists on the 3rd carbon. Let's see what happens if I go in the other direction, and I'm going to change color to make it easier for us to see the difference. If I go in the other direction, this would be my 1st carbon, my 2nd, 3rd, 4th, 5th, and 6th. Notice that this puts the branch at the 4th carbon. I always want to choose the system of numbering so that the branch is at the lowest number possible, regardless of whether I have to start on the left or the right. And once I choose that system, I'm going to use that for numbering all my branches. Obviously, in this case, the 3rd carbon is a better choice than the 4th carbon. So I want to use those numbers on top, not the numbers I had written on the bottom. This means that my branch is located at the third carbon. I'm going to write the number 3 to remind myself of that. Now I'm ready to actually name the branch. When I name the branch, I'm going to do this much in the way that I named the backbone. I'm going to designate how many carbons are present using the prefixes like meth, eth, prop, and so on. So I'm going to use the prefix that's appropriate for this chain or branch length. In this case, I have just one carbon in the branch, so the prefix I'm going to use is meth. However, I don't want to call this methane because it's a branch. It's not its own molecule. Instead, I'm going to use the YL ending. So instead of calling it methane, I'll call it methyl. Notice that I'm separating the 3 and the word methyl with a dash. In IUPAC nomenclature, anywhere that a number and a letter are next to each other, we always separate it with a dash. Now I'm ready to actually put the name together. When I do this, I write the backbone last. I write any branches that are present first. In this case, I have just one branch to write down. So here's what my name will actually look like. 3-methyl, and these can all be lowercase, and it's all one word with hexane. So I would call this molecule 3-methylhexane with a dash between the 3 and the M. Let's try another example. We're going to follow the same 3 steps for this molecule. Take a second, find the molecule if you have the printout, or write it into your notes if you're doing it that way. Make sure you pause the video and try to name this using the same process. My first step is to find the longest carbon chain. Again, I like to do that using a highlighter. Your longest carbon chain can go in any direction. It can go left, right, up, down, and it can definitely bend. Because remember, single bonds can rotate. So how we draw this on paper may have nothing to do with what it actually looks like in 3 dimensions. And because of that, and because this is only the second one you've tried, you may or may not have actually discovered that the longest chain is this. It starts or ends at the carbon that's very low on the molecule, and it moves all the way up through that one that's on the top of the molecule. Notice that this is just a chain. And yes, it has bends in it, but that doesn't necessarily mean it's a branch because it's still one carbon after another. So I'm going to pick that yellow highlighted section as the backbone of my molecule. Did you notice how many carbons it has in it? 1, 2, 3, 4, 5, 6, 7. So I know the base part of my name, or the backbone, is going to be heptane because I have 7 carbons. Now, let's determine the position of the branch. If you got stuck, or if you made a mistake finding the heptane, don't be afraid to pause the video and try again. I only have one branch in this case, and it's located here. I have to decide how to name the molecule, and I really have 2 choices. I have to decide how to number the molecule, and I have 2 choices. I could start here and have 1, 2, 3, 4, 5, 6, and 7. Or I could start here and have 1, 2, 3, 4, 5, 6, 7. The best option is always to have the branch at the lowest number possible. Because the branch is on this carbon, my choices are between numbering it so it's a 5 or a 3. 3 is the better option. So I'm going to call this 3 because it only has one carbon in the branch. This is another example of a methyl. Now I put the name of the entire molecule together, and I'll call it 3-methylheptane. So what happens when you have more than one branch? Well, let's look at some molecules that have that scenario. When dealing with molecules that have more than one branch, you'll actually follow pretty much the same rules. You'll still assign each branch its own name, and you'll still pick its location. Notice that you'll have to number so you get the lowest possible numbers but you can only number once. You can't choose to change direction when assigning these branches. Then when you put the name together, the branches will go in order alphabetically. Let's do this one as an example. Go ahead and pause the video. Okay, so I want to find the longest possible chain. There's a couple different options here. I'm going to choose with just going straight across the top. If you chose to start here and go that way, you'll actually get the exact same answer, which is the correct answer. So this has a total of 7 carbons. So again, I know I'm dealing with a heptane. Now I need to decide where the branches are and what to name them. I always want a number so the branches have the lowest possible number. If I go from the right side, I would have 1, 2, 3, and I would have to start numbering at 4. But if I go from the left side, 1, 2, 3, my branches will start at the number 3. So for that reason, I'm going to number from the left side, and once I've picked that manner of numbering, it's got to stay that way. I can't change it for a different branch. That means that this branch occurs at the 3rd carbon, and this branch occurs at the 4th carbon. Now I have to name each one of the branches. This branch, CH2 and CH3, has 2 carbons. So I'm going to use the prefix F and then add the YL ending, 3-ethyl. This one only has 1 carbon, so I'm back to using methyl. Now when I put this entire name together, I need to make sure to alphabetize the branches. The heptane will always come last, but I have to decide whether to put 3-ethyl or 4-methyl first. The E in ethyl comes first alphabetically over the M in methyl. The 3 and the 4 don't matter. Now when I write this name, I want to make sure I write the branch that has the ethyl first, so 3-ethyl, and then I'm ready to write the branch 4-methyl. Remember, what do we do when we need to separate a letter and a number? Well, we have to write a dash. So I have to write dash before writing 4-methyl. That separates the L and the 4. So I have 3-ethyl, 4-methyl, heptane, and that would be the IUPAC name of this molecule. One thing that can potentially shorten your names is if you have more than one branch that has the same number of carbons. In other words, if I had 2 ethyl branches, 2 methyl branches, 2 propyl branches, or anything in that type. In that case, when you have more than one of the same type of branch, we can actually smush them together a little bit in the name. In that case, we're going to write the location and separate it by commas. And this will look weird until you see it, but the reason it's an advantage is it allows us to use prefixes such as di, tri, and tetra to indicate the number of those branches. We often call those the alkyl names, the branch names, because instead of an alkane with an A-N-E ending, we're dealing with an alkyl with a Y-L ending. Here's an example. Go ahead and try this one. Okay, I want to find the longest possible chain. I like to pick the simplest one, so I'm going to go straight down the middle. I know that that chain is butane because it contains 4 carbons. I have 2 branches. One is this, one is that. This one, if I number the chain, the easiest way to do it is 1, 2, 3, 4, starting on the left. That gives me a 2-methyl, and it also gives me another 2-methyl. The fact that these are both methyls means that I can combine them in the name. And if I do so, it would look like this. 2, 2, indicating that they're both on the 2nd carbon, dimethyl. And finally, the ending of the name would be butane. So there's a couple things I want to point out about this. The 2 and the 2 indicate the location. It's important to use both numbers because even if they were not both on the same carbon, I could have the name written in this fashion. So in this case it was a 2,2 dimethyl, but it could have been 2,3 dimethyl if they were on different carbons. You do need to write both of the numbers regardless of whether they occur on the same or different carbons. If there were 3 methyls, I could have 2,2,2 trimethyl. or 2,3,3-trimethyl, or whatever different one works for the particular molecule. I'm using the prefix di to indicate that there are two methyl groups. Many people find that these start to sound a little redundant. Why do we have to write the number 2 twice when we're also writing the word di? And the answer is, it's basically to ensure that there's absolutely no room for confusing two different molecules. These are classic examples of IUPAC naming because at first when you hear them they seem a little tricky, but once you get the hang of them it's really easy, and the rules won't change much throughout the quarter. We'll just be adding different functional groups to consider. Let's do one more example of an IUPAC naming. Take a second, either look at this on your printout or write it into your notes, and then try giving it a name. Pause the video and restart it when you're ready. There's more than one way to find the longest chain on this one, but I went this way. I started with these carbon, moved through here, and went all the way to the end. You may have also come down to this carbon. It won't make any difference in how you name it. Now I need to locate each of my branches and name them. I have to decide where to start numbering. This carbon or this carbon? Well, if I number with this carbon here, I would have 1, 2, 3. My first branch would occur on a third carbon. If I number from this carbon on the right, I would number 1, 2, and that's where my first branch would take place. I want the lowest number possible, and 2 is lower than 3. So I permanently will number this as 1, 2, 3, 4, 5, 6, 7, 8, and 9. That means that in the end, the name of this molecule is going to be a no name. Now I'm ready to name each one of the branches. This branch has 1 carbon, so this is a 2-methyl because it's located on the second carbon. This branch has 2 carbon, so it's going to be a 6-ethyl because it has 2 carbons on the 6th carbon of the backbone. This branch, my final one, has 1 carbon, so it's going to be located on the 7th carbon, a methyl group. If you got stuck at any point, feel free to pause the video and try writing out this final name completely. Okay, you ready? Here we go. I have 3 different branches to consider: a methyl, an ethyl, and another methyl. E comes before M alphabetically, so I'm going to start by writing the ethyl. I'll call this 6-ethyl. I need a dash to separate it from the next number I'm going to write. Now I have 2-methyl and 7-methyl. Because they're both methyls, I can use the dimethyl shortcut. In fact, I'm required to use that by IUPAC nomenclature. So I start by writing the location of each one of those branches. I have one on the 2nd carbon and one on the 7th carbon, and those are separating a dimethyl, meaning 2 methyl groups. Then I write the backbone, nonane. So the name of this molecule would be 6-ethyl 2,7-dimethyl nonane. One more thing about these. Practice makes perfect on IUPAC nomenclature. You should do as many of these as you need until you're naming the molecules without any question and any mistakes. Another thing is that we will do IUPAC nomenclature in each chapter, each unit, and for every functional group this quarter. It's one of those things that's a little bit like riding a bike. It seems really overwhelming at first, but once you get the hang of it, it's quite easy, and you will be using it so much that you'll be glad you did it. I want to show you one other aspect of IUPAC nomenclature that you may not appreciate. This is a molecule of 6-ethyl 2,7-dimethyl nonane. So are these. Here's all the other ways I could write out that molecule simply by rotating single bonds, which doesn't change anything about the structure. If you were to look at any one of these and use IUPAC nomenclature to name it, by following the rules of always finding the longest chain, always numbering so you get the lowest positions for your branches, you should end up with the exact same answer. And that's one of the reasons that IUPAC nomenclature is so powerful. It allows us to take molecules that might be written in wildly different ways and still determine that they're actually the exact same molecule. Don't put away this molecule just yet, because I want to use this structure to show you one other aspect we often consider in organic chemistry. When we look at the way organic molecules react, their reactivity is often determined by exactly how the carbons within them are bonded. Specifically, reactivity is often determined by how many other carbons each carbon is bonded to. For this reason, we often define carbon atoms on the basis of how many carbons they're bonded to. A primary carbon atom, which can be symbolically written as a 1 followed by a degree sign, is defined as a carbon that's bonded directly to one other carbon. Take a look at this particular structure and find at least one example of a primary carbon. To find a primary carbon, we have to find carbons that are bonded directly to just one other carbon. And the fact is, all carbons that are at the end of a chain or branch are examples of primary carbons because they're directly bonded to just one other carbon. Notice that we consider only what they're bonded to directly, not what proceeds after that carbon in the chain. We also find ourselves working frequently with secondary carbons. A secondary carbon, as you can imagine, is a carbon that's bonded directly to two other carbon atoms. Use this structure to find an example of a secondary carbon. Secondary carbons are always carbons that exist in the middle of a chain. So each one of these carbons is an example of a secondary carbon. Finally, that brings us to a tertiary carbon. A tertiary carbon is a carbon that's directly bonded to three other carbons. There's two examples of tertiary carbons in this molecule. And notice that tertiary carbons are always instances where the carbons are part of a branched system. Technically, there's also quaternary or fourth degree carbons, but they're not as frequently involved in reactions, so we won't run into them frequently. One of the reasons that this primary, secondary, and tertiary determination is important is that we sometimes have to use it in IUPAC nomenclature. So far, our IUPAC nomenclature has included straight-chain alkanes, methane, ethane, propane, and so on, as well as relatively simple branches, like the methyl branch or ethyl branch. These alkyl branches, or carbon-containing branches, do get much more complex. As the branches grow in carbon length, we have more to consider, because we have to look at the options for where the branch will actually connect with the backbone of the molecule. Let's look at propane for an example. We already know that propane as a molecule is an alkane, but let's think about the propyl group. When we think about a 3-carbon branch, its name initially would have to be propyl, indicating that it has 3 carbons. But imagine having 3 carbons linked together. I'm going to leave the hydrogens off just for a second to make this extra clear. If I were to connect this to a backbone, there's 2 different ways it could be connected. One way is that I might have a backbone of the molecule and it could directly connect to the end of this propyl chain. Another way that the propyl chain could be connected would be if that longer backbone was connected to the center carbon. These are 2 different structures, so we need to have a way in IUPAC nomenclature to differentiate between each of these cases. Because of this, there's actually 2 different types of the propyl group. When we connect to the end of a propyl group, this is referred to as an N-propyl group. The N means the simplest form possible. In the case of naming, we actually just call this propyl. So propyl implies that we're connected directly to the end. When we deal with a propyl group that connects through the center carbon to the chain, this is a different structure. This is what's called the isopropyl group. Iso is a prefix that means equal, and in this case, it's really because the branches are equal. The carbon in the middle has 1 carbon on each side. When dealing with the isopropyl molecule, be sure to alphabetize based on the I in iso and not the P for propyl. When dealing with an N-propyl branch, in this case we alphabetize the P for propyl. So you'll either see propyl or isopropyl written into names that have a branch of 3 carbons in length. Let's look now at how this affects 4 carbon branches on a chain. We already know that 4 carbons is associated with the butane name, but when it comes to a branch, we're dealing with the butyl group. The butyl group, if it's connected at its end, again is just called N-butyl, although we only use butyl in the IUPAC name. That means that we directly connect the 4 carbon branch, which basically looks like a chain of its own, at the end carbon. There's 3 other types of ways that you can connect 4 carbons. One is what's called the sec-butyl group. And if you think back to what we just learned a few minutes ago, this refers to a secondary carbon. The way that a secondary carbon exists in the butyl group is not when we deal with a carbon that's on the end of the chain, but rather a connection to the second carbon in the group. The result of this is that we have almost an uneven Y or a T connecting to the backbone. So in all of these cases, your backbone could be a very simple backbone like octane, or it could be a far more complex IUPAC structure. There's also what's called the tert-butyl group. Tert refers to a tertiary carbon. If we write 4 carbons in a chain the way we do for most butyl groups, there is no tertiary carbon. So what the tert-butyl group refers to is 4 carbons as a branch that aren't arranged in a chain. Rather, 4 carbons that are situated in a little bit of a cross or an X shape. In this case, we connect directly to the center carbon. This is what's called the tert-butyl group. One important thing about the sec-butyl and tert-butyl groups, we do not alphabetize the S or the T. Instead, we always alphabetize on the basis of B. So while the prefix iso is used for alphabetizing, the sec and the tert prefixes are not. An easy way to remember this is that you'll notice the iso prefix was written as one word, as in isopropyl, or as we'll see in a second, isobutyl. But the sec and the tert prefixes are offset by a dash. It's important to include this dash, and if we put it into a font on a computer, it's usually italicized, but you don't have to worry about trying to italicize your own handwriting. So this brings us to the final butyl group, the isobutyl group. This looks similar to the isopropyl group, however, because there's 4 carbons, it essentially extends the branch. What it will look like is that we have a carbon connected to a carbon, in turn connected to 2 other carbons, and then our backbone. This is the isobutyl group, and this would be alphabetized on the basis of the I. The butyl, sec-butyl, tert-butyl, and isobutyl groups are important to be able to distinguish between when you're naming IUPAC molecules. Okay, so now it's time for the last topic in this unit, and I thought we'd start it with a quick pop quiz. What is this? Well, about a week ago, you'd probably say that that's a triangle, but since then, you've entered the world of organic chemistry. So you know that anytime we see lines changing direction on paper, it means that there's a carbon atom present. In this case, while the average person on the street would say this is a triangle, you can quickly notice that it actually is a molecule that contains 3 carbons. This particular molecule contains carbon, hydrogen, and single bonds. So it's an alkane, but it's a special type of alkane because it forms a cyclic or ring-like structure. This is what's called a cycloalkane. It's essentially an alkane where one end connects to another. There's many different cyclic compounds in organic chemistry, and cycloalkanes in particular are a good example of a molecule that looks much neater or much cleaner when we draw it as a line structure. It's very easy to name cycloalkanes. We start by considering how many carbons it has and determine what its straight chain form of the name would be. Then we add the prefix cyclo. So in the case of the triangle, which contains 3 carbons, we know that a 3-carbon straight chain alkane would be propane. That means that this cyclic version would be cyclopropane. If I add 1 more carbon, I get a shape that looks like a square. but because it represents 4 carbons, I take the alkane butane and I add the prefix to get the name cyclobutane. I can add another carbon and make cyclopentane, or another to make cyclohexane, cycloheptane, and so on. Not all of these compounds exist in nature, although they're all theoretically possible. And the reason is something called ring strain. When we have these cyclic or ring-like structures, it creates strain on the carbon atoms. Remember, carbons in alkanes have tetrahedral geometry, and tetrahedral geometry has a bond angle of 109.5 degrees. But you might remember from a math class in your past that when we deal with the angles inside of a triangle, we're dealing with a 60-degree angle. That is dramatically smaller than 109.5 degrees, and because of that, it puts a lot of stress or strain on the carbons involved. It's not a very stable compound. That means it's not very likely to exist in nature. The same is true for cyclobutane. The angle in a cyclobutane molecule is slightly larger at 90 degrees, but it's still far off from 109.5 degrees. The 2 cycloalkanes that do commonly exist in nature are cyclopentane and cyclohexane. Exactly what bond angle they have depends on the exact conformation that they're in, but in all cases it approaches that 109.5 degrees. Cycloheptane, on the other hand, becomes much more rare because the carbon is forced to spread its bonds further apart in order to accommodate all 7 carbons. Cycloalkanes are like straight-chain alkanes both chemically and physically. They share many of the same properties. Like straight-chain alkanes as well, cyclic alkanes can have branches that come off of the main carbon structure. We often call these branches substituents. They're fairly easy to name because they follow many of the same rules as naming branched alkanes. When dealing with a cycloalkane that has just one branch, the technical term for that is a monosubstituted cycloalkane. It comes from the meaning one substitution. In other words, one hydrogen has been removed and substituted with a carbon branch. Here's an example of a monosubstituted cycloalkane. To name this cycloalkane, we're going to follow the same steps we used when naming branched alkanes. First, we'll identify a backbone, then we'll identify what the branch or substituent is. First, let's determine what the backbone, or the name of the cycloalkane itself is. How many carbons do you count in this ring structure? 1, 2, 3, 4, 5, 6. These 6 carbons connected together essentially make the backbone, much the same way that we considered when we did naming of branched alkanes. The only difference is we have to remember that it's a cyclic compound, so the name will be cyclohexane. Now I need to add to it the name of the branch. This branch has just one carbon in it, and just like we've seen previously, one carbon in a branch means that I'm dealing with the methyl branch. What's different about cycloalkane naming than branched alkane naming is that we don't need to number the position of this branch. And the reason is it's arbitrary where I can start and stop numbering the ring. This means that the name of this compound would be methyl cyclohexane, all one word and all lowercase. Let's try another one. Name this compound. Pause the video if you need a minute. To name this compound, first I identify how many carbon atoms I have in my ring structure. Here's 1, 2, 3, 4, and 5. Because there's 5 carbons in the backbone, or the cyclic part of my structure, I know the base part of my name is going to be cyclopentane. Pentane comes from the fact that there's 5 carbons. Be careful not to forget the cyclo prefix. It's one of the most common mistakes I see on exams. Now let's talk about the branch, or the substituent, on this cyclopentane. The branch itself is made up of two carbons, one that's directly connected to the ring and one that extends further beyond it. Two carbons is the ethyl substituent, or ethyl branch. That means that the name of this compound will be ethyl cyclopentane. But what happens when I have more than one substituent? When it comes to what are called di-substituted cyclic alkanes, now I will need to number. The rest of the procedure stays the same. Here's an example of a di-substituted cycloalkane. Take a second and at least name the backbone, or the cyclic part of the alkane, and name what each one of those substituents are. Then we'll talk about how to put it together. Okay, so when I look at this, again I have to figure out how many carbons are in the backbone. I look at this shape, and this is a 5-carbon shape, also called a pentagon. My branches are a 1-carbon branch. We know that this is going to be the methyl substituent, and a 2-carbon branch, which is the ethyl substituent. So I know I'm going to have a methyl, an ethyl, and a cyclopentane somewhere in the name. But I have to decide how to actually put this together. And I need to designate where the methyl and the ethyl are. Are they right next to each other on a 1st and 2nd carbon, or are they spread apart? Much like how we decided to number the backbone in a branched alkane, we have some choice about how to number a cyclic structure. We always start by putting the number 1 at the carbon that has the branch that has alphabetic priority. What that means in this case is that I have a methyl branch and an ethyl branch. Because the E in ethyl is before the M in methyl in the alphabet, I'll say that it's attached to the 1st carbon. Now I know where to start numbering. There is not a rule about going clockwise or counterclockwise. Either one can be correct. But just like we saw with the branched alkanes, we want to get the lowest numbers possible. So I have a choice of whether going clockwise, as we number 1, 2, 3, and so on, or counterclockwise. Which one do you think we should do on this molecule? Well, on this molecule, I already have the number 1 in place. To get that methyl group on the lowest possible number, I want to go counterclockwise, because that'll put the methyl at the 3rd position. If I went clockwise in the other direction, it would be located at the 4th position. So I always number so I get the lowest numbers possible, starting with 1 and moving through my other substituent. Now I'm ready to put this name together. Again, we always alphabetize our name. So in this case, we'll have 1-ethyl, 3-methyl, cyclopentane. 1-ethyl, 3-methyl cyclopentane is the IUPAC name of this molecule. Let's try another one. This structure has been drawn entirely as a line structure. That doesn't change anything, but take your time figuring out the correct name. To name this molecule, I'm going to start by identifying what my backbone is, as well as what each substituent is. The backbone, or the cyclic part of the molecule, contains 6 carbons. So I know that that much of the name is going to be cyclohexane. When I look at what the substituents are in this molecule, I have this structure here, and I have this structure here. This is definitely the simpler one. This implies the presence of just 1 carbon. So this is going to have the methyl name. Now I have to look at this substituent. How many carbons do you see in this substituent? Well, there's 1, 2, and 3. We know that 3 means I'm dealing with the propyl name, but wait, we learned that there's a difference between propyl and isopropyl. Which one is this an example of? You can see that the backbone, or the ring, is connected through the 2nd carbon. In other words, it's the middle carbon, and that makes this the isopropyl group. So I have an isopropyl substituent and a methyl substituent on a cyclohexane. Finally, we have to decide how to number this ring in order to get the correct name. Think back and pause the video if you want to how we alphabetize something like isopropyl. Okay, so which should I number as the first carbon? The carbon that touches methyl or the carbon that touches isopropyl? Well, methyl obviously has an M. We do alphabetize the I in isopropyl. If this was a sec-butyl or a tert-butyl, we would be using the B in butyl. But for isopropyl or isobutyl, I use the I from iso. That means this will come first, and it's on the first carbon. When I number around the ring in either direction, I get the same answer. The methyl's on the fourth carbon. So to put this name together, I get the final answer: 1 isopropyl, 4 methyl, cyclohexane. This brings us to the end of this unit. If you haven't already, be sure you're working the recommended problems in the textbook, because that'll give you a lot more practice on these.